Hello, everyone, and welcome to the Circuit Breaker Avail Workshop, Avail 101. Joining us today is QEDK, who will be taking us through the session. And with that, I'll pass it over to QEDK to get the session started.
Everyone, nice to be here. Nice to be chatting with all of you folks. I just ended up sharing my screen because it wasn't working, but I think it's good enough. So yeah, just to introduce myself, hey everyone, I'm QEDK. I'm a senior research and development engineer at Avail. Happy to be here just to kind of give you guys a 101 into how to really start using Avail. So this will kind of serve you when, if, for example, if you have never tried using a DNA before. So let's say that you're starting out building rollups, or like any innovative use case. For example, you might be using Stacker and you might be making micro rollups, or you might be forking CDK and you might be using Avail, maybe to make an L3 valid one. So for those sort of solutions, um, just a sort of a starter into how to use Avail. So the first thing that you sort of need to do on Avail to sort of do anything is to create an application key. And what you do is you're going to give an app key, which is just an arbitrary data. So you can put in something like this, which is just like a random key. And then Avail will generate an app ID for you. And that basically serves as a namespace to separate all the data that you submit to Avail from all the other rollups that are also submitting data. So you can see the encoded call data, you can see the encoded call hash, you submit the transaction. Keep in mind to set the app ID here is 0. So basically app ID 0 here serves, is basically kind of signifying to Avail that, this is not a transaction, it's namespace. So, it doesn't belong to a particular app data. So we just sign and submit this. And then you can see the transaction. We're going to wait for that to get included. So we can see it got included there. Went successfully. We can see our event here. So we'll go to the entire list here, probably mine. And this is, you can see it's our address. And then in this particular event, I can see that an application key was created and it returns this particular app ID, 270 in our case. And this is what you'll be using to submit your data blobs going forward, right? So then we can do another call to the data availability palette, but instead of calling create application key, since we already have a key, basically we already have our namespace for our blob, we can just do a simple submit data. So we can submit a random blob. And here it's a reminder that you should set an app ID here to be the app ID of a namespace that you control. So for example, if someone has reserved the app ID 96, right? Then you cannot post on that namespace. You can only post on the namespaces that you control. So our app ID was 270, so I'm just going to put 270 here so the transaction goes through. So I'm going to sign and submit there and wait for it to get included. So we can see it was included. We go to the Explorer and there are 135 extrinsics in the same block. So good luck, I guess. Okay, somehow we found ours. So we got lucky there. And we can see that the data was submitted successfully. And in the event, we can see the hash of the data that we submitted. And this event signifies that it was submitted successfully. So this would be sort of being the non-programmatic way of submitting data to Avail. But like, let's say you're doing a roll-up or you're doing in bulletin board use cases, as Vitalik likes to call it, then, this might not be perfect for you. In which case, we have examples in the form of, we have Go examples, for example. So we can use something like data submit watch. We have main.go here. And we basically use something called GSRPC. It's basically a Go adapter for substrate RPCs. And since Avail is based on substrate, we have kind of written our own modification called Avail GSRPC that allows you to use our fork of GSRPC in your Go code. So for example, we have GSRPC here, and then we have changed it in the Go mod to use our fork instead. And then you can kind of do all of the things that you just saw me doing programmatically. So you saw, for example, like you have to give it the config role. We create a particular API from the config, we get the metadata, and then we create an extrinsic call to submit data, and then we submit it, basically similarly to what you just saw, with the only exception being creating the application key. But since that's like a one-time process, you don't really need that to be programmatic. And ideally, you should not be creating application IDs more than you kind of need them. So it basically means like if you're running the same rollup, then you should be reusing the application ID. So this is an example code that we have. The repo is Avail project-Avail, and you can find all of this in the examples folder. We also have a couple of other examples. I think the relevant ones will be data submit watch and query proof data. So this is the one that calls Karte RPC to kind of get proofs of the data that you can then prove you're on L1, Ethereum L1 using data attestation. And I guess there's still new blocks, for example, if you want to know what's going on in Avail, if you want to keep track of events, if you want to keep track of bridge events. So these are the Go examples. We also have some Dino examples. These are basically similar to Node, except they're just, we wrote it for Dino. So like if you're using JS environments, like for example, if you're building with Stacker, this would be a good fit for you. Again, as I said, this virtually does the same thing as what I showed you in the Explorer. It's basically submitting a blob of data. And lastly, we have the Validium. These are more like a collection of scripts that particularly do something. So like hypothetically, if you run a Validium that is based on like a TS interface, which is unlikely, then technically you could just reuse this. We basically have functions to get the data route, to dispatch data route into the Nomad bridge, and also function to post the data. And then similarly, we have a couple of contracts here. This is, again, just to keep in mind, this is an example contract. So I'm not going to go ahead and recommend that you use this to run a real Validium, but it's a good mental model for building a real Validium, for example. And that's pretty much it in what we have for examples. I'm going to let Andrew take it away so he can kind of show you a real architecture overview that we have recorded regarding the Avail Validium.
Okay, everyone stand by.
Hi everyone, this will be a short walkthrough of our Avail Validium repositories. So of course, the first thing that we want to look at is the Avail module itself. Just note that since the underlying Polygon CKVM node is written in Go, of course, our implementation or other implementation of that has to be in Go as well. So we have this particular file called avail.go. On the underlying layer, we use something called GSRPC, which is basically Go-based client for working with Substrate. And then we have forked that as well. And so we have our own custom fork of Avail GSRPC that we use to do everything from sending data to querying data to set dispatching data routes and so on and so forth. So let's delve directly into the init function. We basically have this file called avail config. So if we go here and this config.go, what you basically expect is a config file that conforms to this particular struct. So you have JSON, in your JSON you can write seed, and then you can put the seed of the account that we should use to dispatch the extrinsics from. The API URL, basically the RPC URL, the app ID is the one that you'll be creating through create application key. The destination domain will be 1000 for Ethereum. The destination address will be the address of the DA bridge router. And then the timeout will be whatever the timeout you want it to be. We just use it to have sort of a fixed timeline for finalization of your particular extrinsics. Okay, so let's go back to avail.go. In here, what we basically do is we just store all the variables that we'll kind of need to perform repeated queries. So for example, we get the latest metadata, we create the API, we get the config, and so on and so forth. And the reason we do that is so that with every other API call, for example, in post data, we have a couple of other calls as well. we don't really want to incur the cost of this again and again. And then that's pretty much all that we do. So we just set the variables, or like you can think of them as almost global variables here. And so kind of what we're really interested in is this post data function here, right? So what we do is we construct an extrinsic of the DA palette called submit data, and then we just send the TX data, and that's pretty much it. I'll show you as well where we kind of call this submit data in a bit. But yeah, basically what happens is we create this particular extrinsic and we create the signature options, we sign it with our keyring pair, and that's pretty much it. And then what we have is like this, a loop that runs for that timeout period that we specified earlier. And so, for example, if it is in the block, we just submit that as part of the log. If it is finalized, that's when it sort of break out. And this is what kind of timeout is keeping track of. So we just submit a log here, then we hash it, and this transaction hash will become important because we submit it to the ZKVM contract on the L1 layer, whatever that is, to sort of prove that the data that we're saying that we're sequencing is actually being posted to Avail. So with here, what we do is we try to find the extrinsic index so we can keep track of that. We also have the proof as well. We get the header in which we have the block number, and this block number is what you use to kind of fetch the data route from the contract later on. And so we also have this function called dispatch data route, which is doing similar to how post data is sending data in the extrinsic. With dispatch data route, we can give it a header. So you will see we give it the header, we query the header here, and we send it the entire header. And then on the other hand, on the L1 DA bridge order contract, it is able to send that entire data route. So it will basically map a block number to a particular data route. So again, we make a new extrinsic, we get the next nonce, we again craft the extrinsic signature options, and then finally we submit and wait, similar to how we waited for the previous extrinsic. And finally, we have get data. So this is required for our synchronizer. For example, like let's say you're running a new Validium node, right? And then you kind of want to sync your node. That entire process is not that straightforward with the Validium because the data does not live on L1. So what we do is we have this get data function here. And then based on the data that we already indexed from that particular L1 contract, we will be calling, as you can see, we kind of get the block from a full node with the block hash, and then we search for the particular extrinsic where our data is stored, basically. So what we'll then do is that the unsynced Validium node can then sync using the transaction data that are posted to Avail, which then allows you to kind of build trustless sequencer sort of model, so that would not be possible otherwise. And then this is just a helper function that kind of gets the next nonce from substrate. It's pretty trivial. What we are more interested in is basically the finalizer logic. So in the sequencer module, we have something called finalizer.co. And this is where we have sort of readjusted to use Avail. So for example, if I were to show you, let's go to close batch. So we kind of get raw transactions when we encode it. It's basically an RLP encoding of the transactions in a particular batch. And a batch is basically a collection of transaction data across multiple blocks or anything, to be honest. So basically, if the block is non-empty, what we do is we retry Avail 3 times, and then we attempt to post the data. And then we kind of hash it. We store everything related to that particular batch so that we can submit it later. And then we close the batch. So similar to how you would have the normal function ongoing, we just sort of intercept the closed batch flow and we send over the data to Avail. And that is pretty much what we do here. And then, of course, we dispatch the data route as well, so we can access the data later on, or basically we can attest to that data on L1. So that is what we have here. maybe I can show you the sequence sender logic. Here, the logic is sort of complicated, but the thing that you need to understand is now in this sequence sender, what we do is we sort of combine multiple batches and then we start sending them as a batch, as possible as the number we can send, the maximum number we can send in a single transaction. So let's say we have batch X, Y, Z, and we include X and Y, and then the transaction is full. What we do is we just send X, Y with the corresponding sequencing data on L1. And that's basically what is happening here. So as you can see, we have also sent the DA block number, the DA proof, the DA width, and the DA index while we submit a sequence. And that is because of the data attestation function that we have on the L1 contract. So basically what we call your roll-up contracts on L1, which does a data attestation verification. So basically, if you have no L2 data, we don't really care. If you have any L2 data, and then the data route has not been dispatched yet, then we sort of just wait until the data route gets dispatched, because in the optimistic pattern, it can take some time between 20 to 30 minutes to kind of do the entire flow. And then if we observe the data route is already available on L1, then we just append it to the sequence and then we send it. And that's pretty much it on this side of things. We can kind of look into this sequence synchronizer a bit as well. So let's do get data here. That's sort of what we are kind of interested in. Let's say the DA block number for this was 0. So like this is relevant in the case, like let's say you are a roll-up migrating to Avail. Then of course, like your previous sequences will not have any DA block number. So technically what we do is we give it the DA block number, we give it the DA index, and we are able to get the raw transactions from Avail, and we then re-execute the block as if we have the data already. And that's sort of the trustless sequencer model that I was talking about earlier, which a function like this enables through the synchronizer model. And then similar to here, it's basically when we observe the event on L1, we immediately fetch data from Avail, and then we ensure, just for sanity, that the data that we posted is actually correct. So it's sort of like an extra layer of ensuring data availability. So that's pretty much it on the node front. I'll do a short walkthrough to the contracts. So similar to how Polygon ZKVM has Polygon ZKVM as well, we have our version of the Polygon ZKVM, so to say. We can see that we have inherited this DA router verification contract. That's sort of the extra library that we have added. So for example, if I had to show you, let's go to data router verification. Right, so we basically just have a router that we set, and then this is just some simple Merkle root verification, and that's pretty much it. Yeah. So going back to Polygon ZKVM, if you go to sequence batches, that's sort of the important function that we have, where we submit the batch of L2 data, and then you submit the DA data, and then with the DA data, we're able to check for data attestation. So with the block number, the proof, the width, the index, and the batch hash that, if you recall, we submit from the sequence sender, we can indeed prove that some data that we're kind of claiming to submit here has been also posted to Avail. And then basically the rest of the flow sort of remains similar. We have, for example, first batch data as well. We do some comparison checks here. And this is what's important here. This is what's the current accumulated input hash, where we kind of take the batch hash of what we have submitted, and then based on whatever is previously stored in the contract, we kind of create a new accumulated input hash. And this is what the prover is actually proving. It's proving the change from the previous accumulated input hash to the next input hash. So since we proved data attestation at the time of sequencing, we don't really need to post it again at the time of proving. And this kind of helps you save on prover resources, because then the prover doesn't waste its computational resources on basically unattested data or useless data in some form. And that's sort of kind of all the crux of the changes that you have made. As you can see, it's pretty straightforward to implement. We also plan to kind of change this over to use our VectorX bridge, as well as also use the CDK release that will happen in the late February. So this version might kind of change drastically, but from an implementation standpoint, it will kind of remain fairly similar because the code that we have today is forked from Polygon KVM, as will be CDK. So the scope for changes will be quite low in that regard, but still it will be like a decent level change. So you should be technically aware. We'll kind of publish the documentation for the new bridge in the coming days. So you'll also have more clear ideas on what we're doing. And once we have that, we'll also re-implement the Validium with CDK, so to say. And that's the one that will be officially supported going forward. But if you wanted to build a Validium today, this is the solution that you have, and feel free to use it. Yeah, that's pretty much it. Thanks, everyone.
Awesome. Are there any questions for QEDK or QEDK? Anything else you want to maybe share?
Yeah, I think there are a couple of things, like for example, a good question would be like, what can I really build with Avail, right? I think that's what the last question that I see on my screen kind of is.
Yeah.
For example, okay, so just to kind of expand on what I just showed, it's basically an example code for a Validium that is using Avail as its data over there. So it's basically Polygon ZK that has been forked to use Avail as the DNA instead of Ethereum. In short, that's kind of the code that we just walked you through. What we are concerned about primarily in such integrations is how do you integrate Avail in a secure and scalable manner, right? That's sort of what we're looking for. And for example, if you wanted to build a block explorer for Avail, I think that's a valid category. But what really depends in such builds would then become like, how exactly is what you're providing superior to the products that we already have? For example, there is Subscan, and there are a couple of others, open source, and I forgot the one that we're using right now. But it's if you're building something like that is technically innovative, then for sure I think it's something that qualifies. And yes, the technical lift is not trivial, but I think once you get past the initial hurdle of figuring out what Avail is and how do you post data to Avail, I think the use cases become much more common. So if I had to give you some very common use cases, for example, right? A good use case could be like you have Orbit, for example, Arbitrum Orbit, and then you make integration for Avail with Arbitrum Orbit. So just stuff like that, for example, which utilizes Avail. For example, if you're building like a new roll-up SDK, like for example, if there's a competitor, for example, like there's Stacker, who are basically building like SDKs for micro roll-ups. You could leverage that, and then you could build a novel roll-up, a micro roll-up, in fact, that is kind of solving for a particular use case. You could hypothetically, like we also have a tracker word for this, and this can interest some of you, is you can embed the Avail Lite client on like a mobile app. That's something also we're kind of looking forward to. So there are kind of multitudes of use cases. And of course, it might be non-trivial, but this is a long-form hackathon as well as async. So I think it would be a good challenge to go through as well.
Nice, yeah, and I just posted a link that was in the Avail Partner Discord channel that Robin, who is I believe a DevRel from the Avail team, shared as well. So hopefully that people find that resourceful too. Are they any other questions? We're kind of going over a little over, but and if there aren't any other questions, then of course, as I've mentioned before, please connect your dashboard to the Discord channel, or to Discord, excuse me, and then you will be able to access all the partner channels. And like I mentioned, Robin from the Avail team has already kind of sent out a message, to reach out anytime. And I don't know if QEDK, if you're going to be monitoring the Discord channel too, but if you are, then everybody else, you'll be able to see, reconnect with him again.
Yeah, for sure. I'm already on the Discord. I might not be as active because I'm traveling, but I'll try to check in once a day so I can kind of answer your queries. I'm also available on Twitter where I'm more active, if that suits some people. Any resources about data availability? You will find that our docs kind of explain the concepts of DA and also our blog. Let me drop a link to our blog. We actually recently posted about data availability 101. So I think that will kind of help you understand what exactly we're solving for. Let me paste the link here. Yeah, this is the link. And this should be a good explainer into what DA is. So I think that's pretty much it. Just a couple of things that if you're looking to Avail that you should be looking at. So there is Avail sub-XT if you're using Rust. There is Avail GSRPC if you're using Go. And if you're using JS or TS or something like any node runtime, then there is Avail JS SDK. So those are the primary 3 solutions that you have for integrations today. And that should be good enough to sort of get you started.
Awesome. Cheers. Well, thanks again for the great workshop, and thank you all, everybody else, for attending. Just a reminder, hacking starts tomorrow and during the opening ceremony when that begins, so don't miss that. And yeah, hopefully everyone has a great rest of your day, and we'll see you all tomorrow. Cheers. Bye.